So we're just waiting for a switch over of signal inputs from another room in the building. But while that happens, I can introduce our next speaker. I met James, I guess, when social media was like a functioning thing on the internet, I guess. That probably would have been how it happened. When I was an undergraduate, quantum computing was like this magical thing that might work one day. And James was someone who was actually using it like to do real things with. And I was very excited this year to hear that James had moved to a new startup and was doing really, really exciting things. And I'm really glad you're able to join us today. So I won't hesitate any longer and pass over to you.
Thank you. I think I'm being amplified. Let me know if not. I'm James Wootton. I have been looking at the intersection of quantum computing and games for a few years now. And so I'm going to tell you a bit about that, of course. So a bit on who I am. So I have of people working in the quantum computing industry, there's a boring normal background, which is you just go and get a PhD and stuff in a relevant field. And I am one of those people. I'm one of the boring normal people. I got my PhD at the University of Leeds, and then I did more research at the University of Basel. And then I stopped being so boring in 2016 because the kind of research I was doing was for the computers of one day, the quantum computers when they become big, complex computational devices that can do the things that have been promised since the 90s. And what we had in real life were these very simple devices that were in labs, and you couldn't touch it if you weren't a person working at the lab and had a lot of training. So this disjoint, this big distance between what I was doing and what was really available led me to think it's kind of a bit too sci-fi, and I want to do something that's actually tangible to people in the real world. So I made the citizen science game based on my research so that people could actually participate in my research, and this was called Decodoku, and I did this back in 2016. And 2016 was also the year that IBM put a small quantum computer on the cloud for anyone to use. So suddenly they went from being these things that were in labs, and it was very hard to convince anybody to do an experiment if you proposed it, to just being able to do the experiment yourself. So what experiments did I decide to do? I did some real sciencey ones and wrote some papers, but I also thought, let's run a game on it somehow. So this was the beginning of me looking into the intersection of quantum computing and games, and it continued as I went to work at IBM Quantum from 2018 until this year, doing research and education and outreach. And now I'm really focusing a lot more on what quantum computing can do for the creative industries by working at a company that is dedicated to that. And in fact, our headquarters is next door. I don't know which way we're pointing. I think that next door, or maybe over there, in Somerset House, although I'm still based in Basel. Okay, so let's get to what the actual talk is about. Actually, we're not getting to it yet because this is still about normal computers. So I'd like to start with a little bit of context about the history of normal computer games. And so we've got the same image as we saw earlier from Tommy. My first computer was also an Amstrad CPC 464. It's like a sequel. The first games were really more about what computing could do, what games could do for computing rather than what computing could do for games. They were all about showcasing devices, giving people an opportunity to educate people about the devices. So like in 1951, computers were as strange and arcane as quantum computers seem now. So it's part of the job of this Nimrod demo to say, look, here's a computer doing a thing you can understand and giving people a tangible example of what it could do. But then it was not until 1962 that I think you could have something that was really the first novel computer game. So everything before then was an existing game implemented on a computer or an AI for an existing game implemented on a computer. But unless you had a spaceship, you could not play Space War other than by using a computer. So this was also built on a device that was intended for research, and it was built by people who were doing that research, and it was built to demo the technology. But they also had the idea that it should be fun, and it is fun. You can play emulations of this online. It still holds up as a game. But then it wasn't until 1972, which is 10 years later, until you have arguably the first commercially successful game, which is Pong. And so it's interesting to note here that 20 years after games started serving computers, that you get the first game where it's actually worth building a computer just to play that game, and that you can be profitable with it. And it's also 10 years after the first unique game. So we don't expect, when we're repeating this history with quantum computers, necessarily that we're going to start looking at the intersection of quantum computers and games, and immediately this is going to be a profitable venture. We're going to have to go through some of these steps, although hopefully learning from history we can do it a little bit faster. Okay, so I should talk to you a little bit about what quantum computers are, because I guess most of you don't know. I'm not going to give an in-depth explanation of quantum computers, but I want to give at least a little bit of a taste. Basically, they're like conventional digital computers, but quantum. There you go. But one problem we have here is that a lot of you might not know really what conventional digital computers are. So you think of them often, if you think of them even at a high level of abstraction, it might be that you put a problem in and it does some computation and an answer comes out. So then you really don't think too much about what goes on in the middle where you're actually doing the computation. And really that's where quantum computers differ from conventional digital computers, because everything in the middle you don't really think about is different. So if you're not really thinking very much about what normal computers are, then basically quantum computers are the same as normal computers. You give them problems and they give you answers. They differ in what's inside. So what is inside a normal computer? So in quantum computing, we call normal computers classical computers. And basically, you've got a bunch of bits, so zeros and ones. You represent your information with those bits, and then you process that information by means of what we call Boolean logic gates. Well, depending on the way you're actually doing it, maybe you don't actually use Boolean logic gates, but the idea of Boolean logic gates is a model of computation in which you can reason about computing, whether you're physically using Boolean logic gates or not. So what are Boolean logic gates? Well, you've got some examples of them here. One of them is the NOT gate. So you put in a bit, and then you get the opposite bit out. So you put in a 0, you get out a 1. There's also the AND gate. So if you put in 2 bits to an AND gate, then you get 1 bit as an output, and it's basically those 2 bits multiplied together. So if they're both a 1, you get a 1 out. Otherwise, you get a 0. And then you have also the exclusive OR gate. You put 2 bits in, and it will give you a 0 or 1, depending on whether those 2 bits were the same or different. Using basically these building blocks, you can build up any computation. And that is what goes on in that bit that we don't often think about in the middle of a computation. Okay, so what about quantum computers? Well, instead of bits, we have qubits. So we have quantum bits. And we'll get into what the difference is a little bit. But really, the most important thing is quantum bits are still bits. They have values 0 and 1. And still, the computations are made out of Boolean logic gates, but they're just a bit different. So one difference is the gates must be reversible, which means you should be able to deduce the input from the output. So if you take the output of a quantum version of an exclusive OR gate, you should be able to know what you put in. And so the way we usually think about that is that they're done on the bits in place. So you will take 2... I didn't plan the light show, but hopefully it's entertaining. So you take 2 bits, and so these are encoding the 2 inputs that you want, and then you're going to do something to those 2 bits so that one of them, the value gets replaced by the answer of your exclusive OR, and the other one's left alone, and then you can show that That output, which is the combination of one of the inputs and the output you actually want, is reversible. So you're left taking 2 bits and they're somehow disappearing, and then you just get 1 bit come out, but you're operating on these physical bits and you're overwriting one of them with the information you actually want. So this is the kind of thing that quantum gates look like. Another element is that you can do fractions of them, and this is the really quantum part, which I'm going to gloss over, but this is, I'll leave you to look into the details of this. So you can basically do fractions of them. So instead of doing a NOT gate, just turning your 0 into a 1 and your 1 into a 0, you can do something like a quarter of a NOT gate. What does that mean? So it's something you have to do 4 times in order to get a NOT gate. But what does it mean to do 1? It's kind of weird. Does that mean you end up somewhere in between 0 and 1? So therefore, is it like some sort of continuous variable thing, somehow like an analog computation? Well, at least maybe you can see that it's a more subtle gate set. Instead of building your computation out of big Duplo blocks, as you are with normal computers, you're using like Lego Technic, so you can do much better things, right? So that's a kind of very vague, hand-waving, motivating example. The real beauty of quantum computing is where you get into what it means to be able to do these fractional things and how it doesn't mean you're just building an analog computer. It's still digital, and it's using the fact that in quantum systems you can have this wave-particle duality where things are both a wave and a particle, and you're just turning that into a kind of analog-digital duality, which means you get the benefits of both analog and digital computers. So the mystery of quantum computing you'll have to discover on another day, but this is just to give you a sense, a flavor of what goes on. Oh, also another element is that typically the devices look like this grid on screen where you have your quantum bits physically there, and they have their neighbors, and you can only do these logic gates between 2 qubits if they are neighbors, if they're connected on this thing. So you've got these subtleties, these restrictions that you have to live with if you're using a current device. So with that, we can think about the history of this intersection of quantum and games. And here I'm really thinking about actually running games on quantum computers. So one of the first examples was in 2017, which was a version of Battleships. And this version of Battleships, well, like in Battleships, you have to hit a ship a certain amount of times before it sinks. And so I implemented that, but the game mechanic is built on these partial versions of a NOT gate. So every time you hit a ship, it does a partial version of a NOT gate, and therefore you have to do it a few times in order to actually get the NOT gate. So it's built as a kind of motivating example, as a way of explaining quantum gates. It's built with the same sort of philosophy that Nimrod was built back in 1951 as just not a very good game, but as a basis for saying, well, here we can explain something about quantum computing. We can explain something about the principles behind this kind of computation. And then another example in 2017 was a game I called Quantum Awesomeness. So this is because, well, in quantum, we're always trying to say that we've done something good and useful somehow. This is a bar we're trying to reach, and they always come up with names for what it is that they've just achieved. If they've actually solved a big problem that no one else could solve otherwise, they wouldn't need to come up with a fancy name for it, because that speaks for itself. But if you're solving something that's kind of like an impressive problem, you've got to use some branding. So they come up with these things like quantum advantage and quantum utility. So inspired by that sort of philosophy, I called it Quantum Awesomeness. And it's basically a puzzle game. It's based on, so you take the grid that is your actual device, you do a simple puzzle game, and you implement it on a quantum computer, and the quality of the device will affect how hard it is. So if you get some results where you really can't see what's going on, then that gives you the player a nice intuitive sense that this device is a load of rubbish. And if you can play the game quite easily, then you get a nice intuitive sense of this device is pretty good. So this is a way of taking quantum benchmarking of comparing different devices and making it intuitive for people who don't want to learn about randomized benchmarking or other techniques that we can use. So those are just a couple of examples, but there are many more. Those are 2 examples that I did, but there are many more that other people did. And there's a couple of papers that take you through more specific examples of these. But these are mostly games that are serving quantum and not quantum serving games. So these are games to educate, to inform, or they're made by people who are learning. People go to a quantum game jam without knowing any quantum because they want to start learning some principles of quantum mechanics and quantum computing and implementing them in a game mechanic in order to start getting to know what's going on. But what we really want to do, what we really want to move on and find is what quantum can do for games. And so I won't tell you that we're about to be the basis of the AAA industry. This is, we're taking the first steps into this. But this is really something that will be important for us to start looking at. And it's time now. We've done enough. What can games do for quantum computers? It's time to start looking at what quantum computers can do for games. And we have to be realistic about this. So will quantum computers be good for rendering? I would say probably not. Maybe that's just me. Like there's this famous quote from Thomas Watson that he can only imagine there being like 5 computers in the world. So maybe me saying quantum computers aren't going to be good for rendering is going to be as laughable as that in the future. But really, when you use a quantum computer, it's on the cloud, so it's in a quantum data server somewhere, and you've got to ask for your job to be run, and there's currently not a lot of them, so it's got to go in the queue and blah, blah, blah. Doing this lots of times a second is not a thing you should really think about doing. But doing it in a loading screen where the player is expecting to sit there anyway, and you can take a few seconds over asking a complex question to a quantum computer, that's something that we can imagine as being realistic. And so that's the kind of thing we can try to target. So quantum computers will be able to solve optimization problems and constraint satisfaction problems that currently are fairly intractable on a standard computer. So this is the kind of tools that we can imagine trying to bring to people who are designing new techniques for procedural generation to mean that they can do it in a different way than they could do previously. And this is an area which I think procedural generation is really a nice area for quantum computing because there's a lot of things that you can do that count as procedural generation. There's a lot of different computational tasks. Some of them are very easy. Some of them are quite simple. So using a noise function in your terrain generation, for example. And some of them are very hard. You're solving complex optimization problems, or you're finding ways around solving complex optimization problems. So I think it suits the different eras that quantum computing is going to go through. So just a few years ago, the quantum hardware we had, you could emulate it on your phone quite easily, or even an even more simple computational device, like probably the microcontroller in a pregnancy test you could emulate the best quantum computers with a few years ago. So this was a time when emulation could reproduce anything you could do in hardware. Then we've gotten to the point now that there are hundreds of quantum bits, and this is beyond the ability for normal computers to emulate. However, they're a bit rubbish. So you have to be very careful in trying to figure out what problems you're going to try and solve on current hardware. You've got to be very careful about how you tease a result out of it, because it takes a careful hand to use near-term devices. However, you can't emulate them. So it's this interesting area where we know they can do things that can't be done otherwise. It's just really hard to try and figure out how to make them do something that we might want to do. And then in the future, the promised land, the Holy Grail, we're going to have thousands of qubits, and they're going to have error correction that's going to be effectively perfect, and they're going to run all of the big famous algorithms with these massive speed-ups, and we're going to be the basis of everything, and it's going to be a quantum revolution, and blah, blah, blah. So we know in the well, we can hope in the future that that means that with the ability for people, say, working on procedural generation to be able to call these new techniques to solve optimization problems and so on, that quantum computers will be useful for procedural generation and will do things unique to quantum computation for procedural generation in the future. If we can establish even now that thinking in terms of quantum software can give us something that is useful to at least someone, then we set up a nice area in which they're already kind of useful, even if you're simulating it. And then in the future, they're going to be useful, and you're going to be doing things that are unique. So then over time, we can increase the usefulness, increase the sophistication as the technology develops. And this is in distinction to other kinds of applications for quantum computers where they're designed for that area at the end. And until we get there, they can't run. So for example, factoring large numbers and breaking all cryptography and stealing from all of the banks in the world, you can't do that now. And you won't be able to do that with these dodgy devices. It's only when we really unlock the Holy Grail that this will be a thing. And hopefully all cryptography will have moved on by then. And the world won't crumble. Anyway, on that note, so I wanted to establish that we could do something that was useful to at least someone. And this was mostly made as a kind of toy for people to use in hackathons. And it's saying that with even a small number of qubits, quantum is really good at interference patterns. So let's do some interference pattern effect kind of thing. And then maybe that can be used in the same way that people use blur effects in procedural generation back in the 80s. So we're not trying to do anything too revolutionary and too advanced, but we're at least trying to use quantum processes somewhere. We're going to build up these interference effects using the ideas behind quantum software. We're going to run them on a simulator, but at least if that's in some way useful to someone, then this is quantum computers being useful, or quantum software being useful in some limited way. There's a couple of papers listed on screen. I'll just won't go into the technicalities. I'll move on to it being useful. So I used it for some terrain generation, and then I put this in a mine test, which is like Minecraft but open source, and it created an island, and you can explore the island, and that's quite good for saying, look, wow, quantum computers. But what I was kind of surprised by is this has actually become a tool useful for professional people, mostly artists. So there's Libby Heaney, who tried it first at a hackathon and has since used it in her professional art. She was also at Somerset House for a while. Roman Lipsky has also embraced quantum blur as a tool in his art. It's been the main artistic tool he's been using to create his art since 2020. So these are some pictures from an exhibition that he had, juxtaposing some of the classical art that he had before with the quantum blur variations. And then within that exhibition, among the people going around with their champagne is a scientific poster, so I can bore them. It's also been used by an indie game studio. There's a studio in Finland who is using it in a game that's going to come out later this year. I should say, though, that this is a game studio that is really positive about quantum. So they're excited to use it just because it's quantum. And this is a barrier that we have to get through, where people are interested to use it because it's got this nice word that people are interested in. Associated with it. Really, in the end, people should want to use it because it's creating interesting things or useful things for them, rather than just that they like the pictures of the devices that it runs on. So something else that we did in order to actually run things on real devices was this geopolitical map generation. So it's basically you're taking what quantum computers do naturally, which is be a bunch of quantum systems talking to each other, and then saying, can we kind of think of how that could be useful for something? And then I kind of imagined, well, maybe it's like a bunch of AIs talking to each other, playing a game of civilization. So I came up with a way that you have this basically this simplified game of civilization, and it's played by a bunch of qubits. And then you have this interaction where you look at what the qubits are doing, and that influences the moves that are made in the game. And then depending on what happens in the game, you feed that back into the qubits, and then so on and so forth. It's very, very simplistic to call it an AI, especially in such hallowed halls of real AI. But it kind of a first step into how we can start using what quantum computers are now to do something that is kind of a large-scale thing in procedural generation. Another thing we looked into was text generation. So there's a bunch of people who have looked at how to represent text in quantum systems, and they've worked out a way to do classification of sentences with a quantum computer. So we just basically took that and said, well, let's make that into a generator by randomly generating something and saying, oh, I want a sentence about food. Is this a sentence about food? No. OK, I'll change it. And then using the classifier in order to give you a generator. So we've looked a bit into that area as well. Yeah, but this is all prehistory. This is most stuff that I did while at IBM, where looking into quantum procedural generation was not my main focus. But now at Moth, it is. So we're going to really try and expand on this. We're going to look at more creative reuses of what quantum computers can do now and finding ways to shoehorn that into procedural generation, more for fun than for anything else. It's more space war than Pong. And then another thing we're looking at is how to use quantum reservoir computing for procedural generation. So this is interesting because you only need a very small amount of data to train. So instead of taking the whole internet as your training data, you can take like some stuff that you've made and produce new stuff on that. So you're maybe hopefully avoiding some of these legal and moral issues, although that's kind of speculative. And also we want to review the full opportunities of what we are going to be able to do in procedural generation once we get the holy grail of what's called fault-tolerant quantum computation. But yeah, keep up to date with what we're doing if you want to find out more about how we're doing it. So yeah, thank you for your attention.
Wonderful. Thank you so much, James. I think we've maybe just got time for a quick question while our next speaker sets up, maybe.
Thank you so much for the lovely lecture. I'm Aslan, technology scientist, and I'm actually looking at using quantum computing API tools like Microsoft, Google, NVIDIA to run light simulations to get new glass-based chips, because we're moving away from silicon.
Yeah.
Obviously, the climate change is devastating. We've got hurricanes literally every day now. So any thoughts, any advice on obviously running that? I'm using Godot, Unreal Engine, trying to get at least 5. Yeah, any thoughts on glass-based chips to run light simulations and find the optimal design of the glass-based
I think I need more information about the idea of these glass-based chips. So maybe we should talk at lunch. But yeah, sure. Thank you for that.
Yeah, there will be plenty of time to chat as well afterwards. But for now, I think, yeah, let's thank James again.
Thanks.